Every year, over 500 species of bamboo are grown worldwide, and China holds the richest treasure of them all. Imagine this: 16 million acres of lush green forests, an area larger than all of West Virginia, pulsing with life and growing so fast you can literally watch it with your own eyes. Some species can shoot up more than a meter in a single day. This is where a $27 billion industry begins, an industry that feeds, clothes, and even builds entire cities. But behind this green marvel are secrets you've likely never seen. Watch closely. If you stay with this video until the end, you'll discover something that will make you see this simple grass in a completely new light. China is the undisputed king of the bamboo world. The country is home to over 500 bamboo species, and its bamboo forests cover more than 16 million acres. That's more land than all of West Virginia, covered entirely in a sea of green. This massive natural resource is the foundation of a multi-billion-dollar industry. China produces 80% of all bamboo products in the world, exporting them to more than 100 countries. It all starts not in a noisy factory, but in the silence and greenery of endless bamboo forests stretching across southern China. Standing in the middle of one, you're surrounded by thousands of smooth, perfectly straight trunks, reaching more than 100 feet into the sky. Sunlight barely filters through the thick leaves, casting a mystical green glow. And the only sounds are the soft whispers of wind and the gentle creaking of stalks brushing against each other. But bamboo's real superpower is its outrageous, almost indecent speed of growth. It's the rocket engine of the plant world. Some species, like the giant moso bamboo, can grow 3 feet in a single day. Imagine that. You could literally sit and watch it grow. In just a few months, a young shoot reaches full height. It's not a tree that takes decades. It's a giant grass ready for harvest in just 3 to 5 years. And here's the best part. When you cut one stalk, the root system stays alive and immediately sends up new shoots. This isn't deforestation. It's more like mowing a lawn, an endless, self-renewing resource. When harvest time comes, workers enter the forest. There are no roaring chainsaws or heavy machines tearing up the ground. Most of the bamboo is cut by hand, using simple saws or machetes. With a dry crack, the stalk falls to the ground. The branches and leaves are trimmed off, and the smooth, hollow green stems, called culms, are tied into bundles and carried out of the forest. This is the raw material, the uncut gem that's headed to the factory to be transformed into 1,000 different things. Bamboo is a true superhero in the fight against climate change. It absorbs carbon dioxide 35% more efficiently than most trees and produces 35% more oxygen. These 16 million acres of bamboo in China are giant green lungs working to clean the atmosphere. It doesn't need pesticides or fertilizers, making it one of the cleanest crops to grow. And unlike cotton, one of the thirstiest plants in agriculture, bamboo thrives on rainwater alone. Let's look at 2 of the most fascinating transformations. First, how do you turn a round, hollow stalk into a hard, flat floorboard, tougher than oak? The bamboo trunks are first cut into sections and fed into a machine that splits them into long, narrow strips, like a giant apple slicer. These strips still have a curved shape and outer skin. So they go through another machine that shaves off the outside and inside, turning them into perfectly rectangular slats. Next comes a spa treatment. The slats are boiled in hot water or steamed. Not for cleanliness, but to remove all the sugars and starches that bugs and mold love to feed on. After that, the sugar-free slats are placed in a drying kiln, where they're slowly and carefully dried to a precise moisture level. Now we have thousands of perfectly dry, sturdy slats. Time to put them together. The slats are coated with glue and stacked into a mold where a massive hydraulic press comes down. With a force of thousands of pounds per square inch and high heat, it compresses the slats into a solid, monolithic block. From this block, manufacturers cut floorboards, countertops, plywood, and even structural beams. The second transformation is even more astonishing. How to turn this tree-like grass into soft, silky fabric for a shirt or bed sheets. This is industrial alchemy. The bamboo culms are first chipped into small flakes. Then, the flakes are soaked in a chemical solution, usually caustic soda, that breaks down the cellulose, the plant's rigid framework. After several hours of cooking, the hard chips become a soft, thick mass that looks like paper pulp. This pulp is washed, bleached, and pressed to squeeze out excess moisture. What's left is a sticky, dense gel. This gel is then forced through microscopic holes in a metal plate called a spinneret, like a giant molecular meat grinder. On the other side emerge ultra-fine, continuous threads. These threads drop into a bath of another chemical, usually sulfuric acid, which instantly solidifies them. Now we have silky, shiny fiber, bamboo viscose. It's washed, dried, and spun into yarn, which is then woven into incredibly soft, breathable, and hypoallergenic fabric. Now let's peek into the world of small eco-heroes. The birth of a bamboo toothbrush. It all starts with harvesting mature 4-year-old moso bamboo. The trunks are cut, then sawed into long, even sections. These sections are split into thin slats. Next, the slats are run through a special milling machine. Imagine a high-precision pencil sharpener. It shaves the slat into a perfectly smooth, rounded stick, the future handle. This process is incredibly fast, with thousands of handles flying out every hour. Then comes heat treatment. They're baked to make them more water-resistant and to give them a beautiful caramel tone. Next step, the haircut. A machine drills dozens of tiny holes into each handle with surgical precision. Then comes the most fascinating part, bristle implantation. A machine, similar to a high-speed sewing machine, grabs a bunch of nylon or biodegradable bristles, folds it in half, and punches it into each hole using a tiny metal staple like an anchor. This happens dozens of times in seconds. The final touch, trimming. All the bristles pass through a trimmer to make them perfectly even or shaped. And that's it. Simple, brilliant, and much kinder to our planet. But these are just 3 examples. This green dragon has 1,000 faces. Young bamboo shoots are a delicacy in Asian cuisine. It's used to make billions of chopsticks, cutting boards, dishes. It's burned to create activated charcoal for filters. It becomes paper, blinds, furniture, even computer mouse shells. In construction across Asia, it's still used as incredibly strong yet lightweight scaffolding for skyscrapers. And this entire ecosystem, from the farmer cutting stalks to high-tech fabric factories, creates a $27 billion economic phenomenon. But what does that mean? That's more than the GDP of some small countries, like Iceland or Jamaica, and the number keeps growing. Just 10 years ago, the industry was half the size. Projections suggest that by the end of this decade, the global bamboo market could exceed $100 billion, and China plans to stay its dominant player. This isn't just about a few big factories. It's an ecosystem that supports over 35 million people, from rural farmers to designers in Shanghai. It's a story of how nature's wisdom, multiplied by human ingenuity, can turn ordinary grass into an infinite resource that dresses us, feeds us, and builds our world. Think batteries are just boxes that store power? What if I told you it takes nearly 375 tons of rock and over 528,000 gallons of water to produce a single electric vehicle battery? or that 70% of the world's cobalt is mined under terrible conditions, sometimes by children? In this video, you'll learn not just how lead-acid and lithium-ion batteries are made, but also the environmental impact they leave behind. Ready for some shocking facts that will change the way you see batteries? Let's get started. Car batteries are the heart of modern vehicles. They power the engine start, fuel electrical systems, and in the case of hybrids or electric vehicles, are the primary energy source for motion. But let's dive into their origins. The story of batteries begins back in the 18th century. In 1800, Italian scientist Alessandro Volta invented the first chemical battery, known as the voltaic pile, a far cry from the rechargeable batteries we know today. The first rechargeable batteries were created by French physicist Gaston Planté in 1859. These were lead-acid batteries, and remarkably, they're still widely used in vehicles with internal combustion engines today. The modern production of car batteries is a complex, multi-step process that requires precision and strict quality control. Let's break down the details using the most popular types. Lead-acid and lithium-ion batteries. For lead-acid batteries, the primary materials include lead, lead dioxide, sulfuric acid as the electrolyte, and polypropylene for the casing. Lead is either mined from ore or recovered from used batteries. It's then purified and melted for further use. Recovering lead from old batteries is a process that combines engineering expertise with a touch of modern-day alchemy. First, old batteries are dismantled, crushed in specialized machines, and sorted into lead, plastic, and electrolyte components. Think of it as a high-tech blender that breaks everything down into its core ingredients. The lead components are sent to smelting furnaces, where they're heated to temperatures exceeding 1,100 degrees Fahrenheit. At this stage, the metal transforms into a shiny silver stream that's mesmerizing to watch. Impurities and slag are separated, leaving behind pure lead, ready for new uses. The purified molten lead is poured into molds, where it cools and solidifies into perfectly uniform ingots. These ingots form the foundation for new batteries. The most fascinating part? This lead can be recycled endlessly. It has already lived in previous generations of batteries and might just end up powering your car. Lithium-ion batteries are made from key components like lithium, nickel, cobalt, manganese, graphite, and an electrolyte. Lithium is sourced either from salt flats in South American countries like Chile and Argentina, or from ore deposits in Australia. For lead-acid batteries, the electrodes are crafted from lead plates coated with active materials, specifically lead powder and lead dioxide. Picture this. Molten lead is poured into molds or rolled into thin sheets, which are then cut into precise shapes. These plates often feature multiple holes or grids to enhance bonding with the active material. The active material, which coats the grids, is prepared as a thick paste made from lead powder, water, sulfuric acid, and additives that enhance the chemical reactions. Let's take a closer look. The powder is produced by oxidizing lead in specialized mills, which grind it into a fine dust with the required properties. Watch as the grids move seamlessly along an automated conveyor, where the paste is applied to both sides. Rollers in the machine press the paste into the grids with just the right amount of force, ensuring even coverage and deep penetration into the cells. Excess paste is scraped off with blades, leaving a perfectly smooth layer. These paste-coated grids are then sent into special drying chambers. Inside, the paste loses moisture and hardens, transforming into the active material. We've covered lead-acid batteries. Now let me show you how lithium-ion batteries are made. In lithium-ion batteries, the anodes are made from graphite, while the cathodes are crafted from metal oxides, like lithium cobalt oxide. Next comes the assembly of the battery cells. These are the basic building blocks of the battery. In lead-acid batteries, cells are made by stacking several plates separated by separators. In lithium-ion batteries, the cells can be cylindrical, prismatic, or in pouch cell form. Electrolyte filling is the next step. In lead-acid batteries, a sulfuric acid solution is poured in. For lithium-ion batteries, an electrolyte made from organic solvents ensures the transfer of ions between the electrodes. The finished batteries undergo an initial charge to activate the chemical reactions. Each battery is tested to ensure it meets key parameters such as voltage, capacity, and resistance to discharge. Lead-acid batteries are then encased in polypropylene shells. Lithium-ion batteries, on the other hand, are often assembled into modules, which are later integrated into large battery packs for electric vehicles. Battery production is an energy-intensive process with significant environmental impacts. While lead can be smelted and reused, plastic casings are recycled into new shells, and the electrolyte is neutralized or processed. The situation with lithium-ion batteries, however, is far more challenging. Only about 5% of lithium-ion batteries are recycled. This is due to the complexity of extracting lithium, nickel, and cobalt. But the damage doesn't stop with neutralizing the components. To produce a lithium-ion battery for an electric vehicle weighing about 1,100 pounds, it takes 550,000 pounds of rock and nearly 530,000 gallons of water. This depletes Earth's precious resources. Producing just one EV battery generates anywhere from 3 to 16 tons of carbon dioxide. Imagine that. This is the same amount a gas-powered car emits over 5 years of driving. And that's just from one battery. The most troubling issue, however, is cobalt mining. About 70% of the world's cobalt comes from the Democratic Republic of Congo, where workers, including children, labor under horrific conditions. According to Amnesty International, more than 40,000 children are involved in cobalt mining. To make matters worse, mining often destroys local ecosystems, leaving lasting environmental damage. Recycling lead-acid batteries in countries with low environmental oversight, such as India and China, presents its own set of dangers. Lead dust and acid emissions often escape into the air, creating toxic clouds that harm the health of hundreds of thousands of people. Every single day, millions of batteries end up in landfills, posing a serious threat to the environment. But what if I told you those old batteries hold rare metals that can power the technologies of tomorrow? Lithium for electric vehicles, nickel for wind turbines, cobalt for medical devices, all hidden within the process of recycling. Want to know how toxic waste transforms into resources for the future? Stick around, an incredible process awaits. Battery collection starts with people. Individuals drop off batteries from phones and laptops. Auto repair shops contribute electric vehicle batteries, and businesses with lots of equipment also pitch in. Collection points can be found in electronics stores, supermarkets, or specialized recycling centers. This process is mostly hands-on. People bring in batteries, and staff or volunteers accept and log them. Large volumes of batteries from factories or auto repair shops are delivered by trucks to major collection centers. Specialized battery containers come equipped with sensors to detect their fill level. When a container is nearly full, it sends a signal to the recycling company. Some companies even use drones to check the status of large containers in remote locations. Batteries are sorted by type using both people and machines, as different batteries, like lithium-ion, nickel metal hydride, or lead-acid, can't be recycled together. At smaller collection points, like those in cities, workers manually sort batteries by examining labels, markings, and physical characteristics such as shape or color. Small batteries from smartphones or laptops are sorted one way, while larger electric vehicle batteries take a different path. At larger facilities, automated sorting lines take over. Machines scan batteries based on their size, weight, and the metals they contain. Advanced tools like X-ray analysis or spectroscopy determine the type of battery in front of them. Once scanned, batteries move along conveyors into designated bins, where they wait for the next stage. Even at automated factories, people are still part of the process. Operators ensure machines are sorting batteries correctly. If a problem arises, like a damaged battery case or missing label, workers step in to sort them manually. Batteries from electric vehicles or solar power systems are often too large for automated lines. This is where robots come in, helping dismantle these massive units into smaller sections, which are then sorted by material. No matter how much machines can do, people are still the heart of the sorting process. Most of the work is handled by employees at collection points and operators of sorting lines. Experts manually inspect damaged batteries because machines haven't yet mastered the ability to detect every defect. Sure, machines are faster, but we can't do without human oversight just yet. In the end, every properly sorted battery is another chance to recover rare earth metals and reduce environmental harm. Next up, the batteries get shredded, like entering a pair of massive steel jaws. They're loaded into a machine that looks like a giant shredder, armed with industrial-grade steel blades. These blades are so powerful they can tear apart an electric vehicle's battery casing. The scene is pure metallic chaos. The sound of ripping, grinding, and snapping as the batteries are literally torn to pieces. Since batteries may still hold a charge, they're first frozen in liquid nitrogen. This cools the metals and minimizes the risk of fire. Some shredders operate in sealed chambers filled with inert gases to prevent contact with oxygen. There's even a more dramatic approach. In some facilities, batteries are burned with controlled electrical currents, leaving only the metals behind. The batteries are shredded into pieces ranging from several inches to fine powder, depending on the type of shredder. The blades spin at over 2,000 revolutions per minute, sending metal fragments clanging and crashing inside a protective chamber. The shredded material then moves through magnetic separators, which precisely extract ferromagnetic metals like nickel or cobalt. The remaining fragments continue along the conveyor belt. A fine black powder, known as black mass, settles into specialized containers. This is where the real treasure lies: lithium, cobalt, and manganese. Machines use dust collectors to literally suck up the powder, ensuring even the tiniest particles are recovered. The remaining materials that can't be recycled, plastics and traces of electrolytes, are flushed out using specialized liquid streams. At this stage, hydraulic crushers grind the leftovers into a slurry that's easy to filter. Engineers monitor the crushers and the temperature inside the chambers. Specialists analyze the crushed material to ensure all metals have been separated and no unwanted contaminants remain. If a battery is still charged or has defects, it can literally explode during crushing. But don't worry, the system has it under control. Any explosion is immediately suppressed with gases, and the process keeps running smoothly. Once the batteries are shredded and that precious black powder is collected, the real magic, science in action, begins. Metals that seemed locked away forever are recovered using two main methods: hydrometallurgy and pyrometallurgy. It might sound a bit technical, but the processes themselves are fascinating. So, how does it work? The battery fragments are submerged in special acidic solutions. Imagine massive vats filled with bubbling yellow-green liquid, typically sulfuric or hydrochloric acid. When the fragments are immersed, a chemical reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve into this metallic soup. To extract specific metals, a clever trick called ion extraction is used. Special reagents, such as organic compounds, are added to the solution. These reagents act like magnets, binding to particular metals. The result? Each metal settles into a separate layer. Once the metals are isolated, they're precipitated as salts or hydroxides. These appear as tiny white or colored crystals. For example, lithium settles as lithium carbonate, resembling fine sugar. Cobalt forms a vibrant blue precipitate, while nickel becomes a pale green powder. If hydrometallurgy is the gentle approach, pyrometallurgy is more like shock therapy for metals. Everything here burns and melts. The black mass is loaded into a massive electric arc furnace, where temperatures soar to nearly 3,000 degrees Fahrenheit. The metals liquefy into molten layers, while plastic and other remnants simply burn away. The metals separate naturally, like oil and water, but at lava-like temperatures. Inside the furnace, several layers form. Heavy metals like cobalt and nickel sink to the bottom, while lithium remains in the slag, the lighter, upper layer. This slag is then broken apart and processed separately to extract lithium. Once cooled, the metals take the form of small ingots, shiny, smooth, and ready for reuse. Cooling after the pyrometallurgical process is typically a controlled procedure. If molten metals are left to cool on their own, it could take hours or even days. Plus, uneven cooling can lead to structural irregularities, which compromise the quality of the final product. That's why specialized chambers are used to regulate the cooling speed. For air cooling, ingots are placed on a conveyor under powerful fans. Imagine a giant hairdryer quickly cooling the metal surface. For water cooling, the ingots are submerged in tanks filled with water or special liquids for a faster process. As the red-hot ingots hit the water, they release dramatic clouds of steam, a visually stunning sight. There's also hybrid cooling, where the process starts with air cooling and finishes with water immersion. This method reduces internal stress in the metal. Controlled cooling ensures a uniform metal structure, which is critical for reuse in batteries. It minimizes cracks or defects that can occur due to rapid temperature shifts. The extracted lithium is used to create new batteries, ones that will power electric cars or even your phone. Nickel becomes part of wind turbines generating clean energy, while cobalt plays a vital role in medical devices. This process literally closes the loop. Old batteries give life to new technologies. Discarded batteries can become an ecological disaster. First, they contain toxic substances that contaminate soil and water. Second, mining for new rare earth metals not only depletes natural resources, but also damages the environment. Recycling solves both problems. Here's the kicker. The more batteries we recycle, the less we rely on mining new materials. It's a direct path to sustainable development. Despite lithium's growing popularity, only 1% of this metal is currently recycled. The main reasons: high costs and the complexity of the process. But researchers are developing new technologies that could revolutionize this in the coming years. Interestingly, even now, electric vehicle manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plants to keep control over these valuable materials. You wouldn't believe how much technology goes into making ordinary toilet paper. Robots cutting trees with laser precision, machines rolling them out at speeds of hundreds of miles per hour, and even artificial intelligence monitoring every single inch for quality. After this video, you'll never look at toilet paper the same way again. Watch till the end. It's going to blow your mind. Let's dive right in. The process starts at logging sites, where machines known as harvesters are used. These impressive machines cut down trees, strip them of branches, and chop them into logs of precise lengths, all in one go. Honestly, I could use something this multifunctional for cleaning my house. Logging is meticulously planned, using GPS and GIS to identify optimal areas for cutting while adhering to strict environmental standards. Trees are harvested selectively to prevent over-deforestation. Logs are then transported to pulp mills by specialized trucks equipped with GPS trackers that optimize delivery routes. Alongside fresh wood, these factories also use recycled paper, collected through recycling programs, delivered as compacted bales. At the mills, the logs are fed into automated lines, where they're chipped into small, uniform pieces. See how tiny these chips are? That's thanks to industrial-grade chipping machines, equipped with sensors to control wood size. These chips are moved along automated conveyors to massive digesters. Before entering the digester, the chips pass through magnetic separators to remove any metal and sieves that ensure uniform size. Sensors and computer systems manage every stage. Inside the digester, the chips are mixed with chemical solutions like caustic soda and sulfides, a process called the Craft method. Automated dispensers precisely measure and add chemicals based on the type of wood being processed. Feeling the heat yet? Inside the digester, the chips are heated under high pressure for several hours. This entire process is automated. Computer systems carefully control temperature, pressure, and cooking time to produce the perfect consistency of pulp, a mixture of solid particles and liquid. Now, check this out. The pulp is pumped into centrifuges, which remove heavy impurities like stones, sand, or metal. Chemicals are then added to break down any remaining linin, the substance that binds wood cells together. Advanced sensors monitor temperature, pressure, and chemical concentrations to achieve optimal pulp brightness without wasting reagents. After this, the pulp is washed to remove residual chemicals and byproducts. Multi-stage washing systems clean and recycle water, minimizing waste. Oh, you're still here? Great. Quick story. One Halloween, I was completely swamped with deadlines. Instead of competing in our neighborhood's annual Best Holiday Decorations contest, I gave up. In a moment of pure laziness, I TP'd my own house, just like in those classic prankster movies. Surprisingly, it got more compliments than any decor I'd ever done. The irony, right? Anyway, back to business. Once purified and bleached, the pulp, which now has a creamy consistency, is piped to forming machines. Sensors installed in these pipes monitor temperature, moisture levels, and pulp density. The pulp is spread onto a forming table, the core component of the paper-making machine. This section consists of an endless wire mesh, moving at speeds of up to 63 miles per hour. The pulp is evenly distributed onto the mesh through nozzles, and excess water is removed immediately using vacuum pumps. The sheet then moves to the press section, where special rollers covered with silicone or rubber squeeze out more moisture. Next up, drying. The sheet passes through a giant cylinder known as the Yankee dryer, heated to temperatures between 240 and 300 degrees Fahrenheit. By the end of this stage, the paper's moisture level drops to around 5%. Sensors constantly monitor the cylinder's temperature and rotation speed to prevent overheating or overdrying. Now for the finishing touches. The dried sheet undergoes embossing, where textured patterns are pressed onto its surface. This step enhances the paper's softness, absorbency, and appearance. Steel or rubber rollers with intricate designs create these patterns. Automated systems ensure the patterns are crisp and evenly applied. Some manufacturers add fragrances or moisturizing agents at this stage, spraying them on in thin layers using advanced nozzles. Optical and ultrasonic scanners monitor parameters like thickness, density, and uniformity. If defects such as tears or uneven textures are detected, the system automatically adjusts or discards the flawed section. Data from all scanners is fed into a central computer, analyzing the entire line's performance in real time. It can even predict potential issues, like roller wear, and notify operators for maintenance. Cool, right? After forming and drying, the paper is rolled into massive jumbo rolls. These rolls can measure several feet wide and weigh hundreds of pounds. Robotic arms transport the jumbo rolls to the rewinding section, where the sheet is unrolled, smoothed, and prepped for cutting. Rewinding machines stretch the paper and roll it onto cardboard cores, which are automatically fed into the line. Check this out. These machines can wind hundreds of rolls per minute, and they're constantly monitored for tension or defects. If something's off, the system pauses to prevent waste. Once rewound, the rolls move to the cutting section. Here, larger rolls are sliced into smaller, standard-sized rolls using high-speed cutting machines. Titanium or steel-coated blades ensure clean, precise cuts without damaging the paper. These machines operate with millimeter precision, guaranteeing uniformity. Automated systems monitor blade sharpness, replacing dull blades without interrupting the process. Each roll undergoes final inspections via high-resolution cameras and infrared sensors, checking diameter, density, and cut quality. Defective rolls are swiftly removed using pneumatic arms. Finally, the finished rolls head to the packaging section. Robotic systems handle them without contact, reducing contamination risks. Sensors align the rolls before they enter the wrapping machine, while a computer system ensures all rolls meet size and weight standards. The rolls are grouped into packs, 4, 6, 12, or even 24, based on consumer demand. Robotic arms stack and wrap the rolls using either thin but durable plastic film or eco-friendly paper packaging. This ensures protection from moisture and dirt while catering to environmentally conscious buyers. Hey bro! Today, we're diving headfirst into the wild world of money. Straight to the US Bureau of Engraving and Printing. That's the spot where real deal dollars are born. The ones that end up in people's pockets and keep the global economy humming. But listen, these aren't just some random pieces of paper with numbers slapped on them. Every bill is a legit masterpiece, packed with cutting-edge tech. We're about to uncover the secrets behind that one-of-a-kind paper, the mind-blowing microscopic details, and the top-tier security features that make the dollar untouchable. You ready? Let's roll. This is gonna be epic. First off, forget about regular paper. Dollars are printed on some next-level stuff made by Crane and Company. This isn't your basic white office paper. It's a cotton linen blend with a unique texture that's totally different from the usual. That's why dollars have that crisp crinkle and last way longer. The material is 75% cotton and 25% linen, with tiny colored fibers woven in that you can only spot under a microscope. Plus, the paper is packed with watermarks and embedded security threads, making it nearly impossible to fake. This paper gets delivered in massive rolls, each one guarded like it's gold. And boom, that's step one in the battle against counterfeiters. Now we're stepping into the engraving department, the place where the magic happens and the main design for each bill is born. This is where artists, known as engravers, carve out the intricate designs and portraits by hand on metal plates with jaw-dropping precision. Take those iconic presidential portraits, like George Washington on the $1 bill or Benjamin Franklin on the $100 bill. They're painstakingly recreated from photographs. And those lines that look straight? They're actually made up of microscopic details. That's another layer of protection. No regular printers pulling that off. Feeling a little outclassed? Don't sweat it. This stuff is straight up genius. Next up, we're heading into the heart of the factory, where the real magic of printing goes down. Check out those massive printing machines using the intaglio technique. That's fancy talk for deep engraving. Here's how it works. The metal plates made by the engravers are coated with ink, and then the excess is wiped off, leaving the ink only in the engraved grooves. The paper is then pressed onto the plate under insane pressure, transferring the ink onto it. Thanks to intaglio printing, certain features on the bills, like the portraits, have a raised texture you can actually feel. How cool is that touchable detail? This process happens multiple times because dollars are printed in layers. First comes the black ink, then green, and finally, other security features are added. Every year, they crank out about 7 billion bills here, with 95% replacing old or worn-out cash. Oh, and the ink? It's so tough that even if you bury a dollar bill for 20 years, you'd still be able to recognize it. In today's world, where counterfeiters are getting slicker by the day, money has to level up with serious protection. For instance, there's microprinting, tiny text you can only see with a magnifying glass, added around portraits or borders of bills. It's so small and detailed, it's practically impossible to fake. Then there are those special security threads embedded in the paper. Under ultraviolet light, these threads glow in different colors depending on the bill's value. For example, $5 glow blue, while $100 shine pink. And let's not forget the $100 bill. It's loaded with high-tech features like 3D holograms that shift and change depending on the angle you look at them. How's that for next-level security? Next stop, the offset printing section. This is where those background images, like the green and golden hues you see on dollars, are added. It's the second line of defense. Intricate patterns and color gradients that are almost impossible to replicate with basic tools. Rolls of future cash spin on cylinders, feeding into the printing machine. Once the ink is applied, the rolls are cut into sheets of the perfect size. Fun fact, a dollar bill lasts on average 5 to 8 years before it's retired. On the back of the $1 bill, you've got the pyramid symbolizing strength and durability, while the all-seeing eye represents divine protection. Pretty wild, right? Let's keep this tour moving. Bro, now we're in the room where dollars get their names. This is where each bill gets its unique serial number, printed in either black or green ink. It's basically the ID code for every single banknote. The next step? Stamping the Federal Reserve seal. These seals show which of the 12 Federal Reserve banks issued the note. This whole process happens on high-speed printing machines that churn out thousands of bills per minute. And get this, the printing conditions are no joke. The machines apply 80 tons of pressure, and the wax-based ink is literally baked into the paper under high heat. The ink is specially designed to resist wear and tear, even something as wild as going through the wash. Oh, and here's a crazy stat. The total value of all cash dollars in circulation is over 2 trillion. How's that for some money talk? Before dollars leave the factory, they go through some hardcore quality control. High-tech scanners check every single bill for defects. Blurry ink, damaged paper, or misaligned designs. If there's any mistake, the bill is pulled out of circulation immediately. The ones that pass, they're neatly packed into stacks of 100 bills. The final step is packing the money. These stacks are loaded into special containers and shipped off to Federal Reserve banks. From there, they make their way to commercial banks and eventually into people's hands. The whole transportation process is locked down tight, with heavy security. We're talking millions of dollars here after all. When a bill is declared too worn out, it gets destroyed. Don't get teary-eyed, bro. Let's check out how it happens. Worn-out banknotes are tossed into industrial shredders that chop them into tiny bits. According to the Federal Reserve, around 5 billion bills are shredded every year, mostly $1 and $5 notes, since they take the hardest beating from daily use. But shredded cash doesn't just get thrown away. The Federal Reserve is big on keeping things eco-friendly, so they find ways to repurpose the materials. Here's a funny story. One time in Texas, some clueless criminal broke into a Federal Reserve facility, thinking he'd hit the motherlode. Instead of stacks of cash, though, he walked off with a giant bag of shredded money. Thinking he'd scored big, he dragged his loot home. Spoiler alert, shredded cash is worth zilch. The guy got caught within a day. Tough luck for him, but at least we got a good laugh out of it. In some states, shredded bills are pressed into dense briquettes that are used as fuel for energy production. Pretty cool, right? This process replaces wood or coal, cutting down on environmental harm. In areas with the right tech, the shredded cash can even be turned into compost, since cotton linen paper is biodegradable. Yeah, money literally gets buried in the ground. A portion of the shredded banknotes is also repurposed into souvenirs. For example, they're packed into clear balls or boxes and sold to tourists at gift shops in the Bureau of Engraving and Printing. It's a unique way to hold a piece of money history in your hand. So, how about it, bro? Want to snag a chunk of chopped up cash for your shelf? Destroying large sums of cash is a whole other level of operation. When entire series of banknotes are pulled from circulation due to design updates or new security features, the disposal process gets even more intense. The old bills are transported in armored vehicles under strict surveillance, and every step of the destruction process is carefully documented to make sure not a single bill ends up in the wrong hands. This massive operation is actually cost-effective in the long run. For instance, according to the Federal Reserve, the cost of destroying a single bill is just 0.03 of a cent thanks to automation. Every day, up to 200 tons of banknotes are shredded across the US. Even the machines used to destroy bills are guarded as tightly as the money still in circulation. It's a big deal, but hey, with that kind of precision, counterfeiters don't stand a chance. When it comes to durability, $1 bills last about 6.5 years on average, while $100 bills can stay in circulation for up to 22 years since they're handled less often. Not bad, bro. especially when you compare it to the lifespan of large denomination euro bills, which is only about 5 years. So, how do they decide when it's time to retire a bill? That's where the Federal Reserve's specialized machines come in. These machines assess the condition of banknotes and flag the ones too worn for circulation. But here's the kicker: the actual disposal doesn't happen at the same place as the printing. The Bureau of Engraving and Printing only destroys defective bills that pop up during production. For example, if the ink isn't applied evenly or the paper gets damaged, those bills are immediately shredded. Quality control on point, right? A few years back, a group of criminals in the US decided to rob an armored truck carrying cash. They planned the heist down to the last detail, but they picked the wrong moment to strike. Instead of shiny fresh bills, the truck was hauling worn-out banknotes headed for destruction. The plan might have seemed genius at first, but the payoff? Practically worthless. Talk about a major flop. Then there's the classic case of the thief who tried to snatch some cash from a bank. In his rush to get out, he grabbed a bag full of bills, completely clueless that it was rigged with dye packs. The second he stepped out of the bank, boom! The capsule exploded, covering both the cash and the crook in bright, unmistakable dye. Those bills became totally useless, and the mastermind left a literal trail of evidence straight to where the cops nabbed him. Honestly, I bet that trail wasn't just bright red or purple. There was probably a little brown in the mix too. Not that the press would mention that part. Have you ever wondered how many times aluminum can be recycled? Imagine this. One can you drank from today could be back on the shelf as a brand new can in just 60 days. And here's a jaw-dropper. Over 120,000 aluminum cans are used every minute worldwide. But wait, there's more. In the United States alone, enough cans are recycled each year to cover 3,000 football fields. Why is recycling aluminum so critical? How do these tiny metal heroes make such a massive impact on the planet? Let's dive into this video where every statistic amazes, and the transformation process will leave you inspired. The journey of recycling aluminum cans starts with collection, a crucial step in the recycling chain because timely gathering of raw materials ensures efficient processing later on. Most aluminum cans are collected through specialized waste collection systems in cities and communities. Many countries have waste sorting programs encouraging consumers to deposit empty cans in dedicated metal recycling bins. In the United States, there are widespread redemption centers where consumers can return used cans for a small cash reward or discount, incentivizing eco-friendly behavior. These programs are also common in parts of Europe and Australia. Some regions even organize campaigns where individuals can bring used cans to special recycling stations, making it easier to gather metal waste while reducing environmental pollution. Globally, about 120,000 aluminum cans are used every single minute, a staggering number that highlights the importance of efficient recycling. Many stores feature special bins for collecting empty aluminum cans, especially in areas with popular deposit systems where consumers can return packaging for a refund, often earning a few cents for each can. Beverage manufacturers and packaging companies also participate in the recycling process by sending metal waste from production to collection centers. This applies to used cans and leftover aluminum elements from the manufacturing process. Some recycling systems even include automatic waste sorting at the collection stage. Advanced technologies like magnetic separators are used to extract aluminum from other metals and plastics efficiently. In regions without such systems, manual sorting is still the norm. In the United States, the aluminum can recycling market is valued at over $1 billion annually. This massive industry injects revenue back into the economy, fueling businesses that recycle and produce new products from repurposed metal. Once collected and sorted, the cans are transported to a recycling facility, where they're stored in massive containers or warehouses until processing begins. The entire recycling journey of an aluminum can take less than 60 days, from the moment it arrives at the facility to the moment it's transformed into a brand new product. That means the can you finished today could be back on the shelf in just 2 months. To ensure a smooth process, cans must be kept separate from other waste materials, so they're often stored separately. Before moving on to further processing, the cans undergo a thorough cleaning. This includes washing off any leftover liquids, removing labels, adhesives, and other contaminants that might still be on the packaging. And now for the most epic part, shredding. Once cleaned, the cans are shredded into small pieces using industrial shredders or other mechanical equipment. This step drastically reduces the volume of the material, making it easier to process. What's left are aluminum shreds, or chunks, ready to be transformed into new products. I've got to say, being there for this part was nerve-wracking. It felt like one of those shards might fly off and hit me in the eye. And the noise, the grinding and crunching were absolutely deafening. Hot. Insanely, blisteringly hot. That's how it felt when we approached the smelting furnace. The shredded aluminum pieces are sent straight into it. 1,220 degrees Fahrenheit, a temperature so intense, it's surprising it's not 1,222 for some devilish symmetry. Melting is the key stage where the metal is heated until it turns liquid. During this process, any remaining impurities and other materials are burned away, leaving behind pure aluminum ready for reuse. Watching it felt like witnessing the Terminator's final moments. I swear. The team explained to me that smelting is energy intensive, but even with the high energy consumption, this process is far more efficient and less costly than extracting virgin aluminum from ore. The molten aluminum from the furnace is poured into molds to create ingots, wire rods, or sheet metal. These aluminum ingots, known as slabs, are massive blocks that are easy to handle during later processing stages. Each slab measures several yards in length and about 2 feet thick. Once cooled and solidified, this metal is ready for a new life, whether as fresh aluminum cans, car parts, construction materials, or other products. Here's the incredible part. This process can be repeated endlessly. Aluminum can be recycled over and over without losing its quality. Imagine that. Cans can go through the recycling loop dozens, even hundreds of times. It doesn't wear out from remelting. Honestly, it feels like we were lied to. Terminator had to be made of aluminum, folks. Now, what are these wire rods, you ask? Fair question, and I've got the answer for you. Wire rods are a form of aluminum created after the molten metal is poured and shaped into thin wires or rods. After smelting, the liquid aluminum is cast into molds for further processing. The metal is rolled into large wire rods using specialized rolling mills. These mills reduce the cross-section of the metal and shape it into the desired form by passing it through rollers. The rods can then be cut into smaller sections or sent off for additional processing to create a variety of aluminum products. In the end, wire rods are the foundational form of aluminum used to manufacture new products. This keeps the recycling and reuse cycle going strong. The diameter of aluminum rods can vary depending on their intended purpose, typically ranging from 0.04 of an inch to 0.75 of an inch. However, this can change based on production specifications and the final application. Thin wire rods, with a diameter ranging from 0.04 to 1/10 of an inch, are commonly used to make wires, electrical cables, or delicate metal components. Medium wire rods, measuring 1/16 to 0.4 of an inch, are suitable for sturdier products like structural elements, or, in some cases, new aluminum cans, when further processing requires that specific diameter. Thick wire rods, over 0.4 of an inch in diameter, are reserved for heavy-duty applications such as the automotive industry or the production of large structural components. Each type of wire rod has its own specifications and undergoes additional processing depending on the final aluminum product being manufactured. To produce aluminum sheets, the slabs are gently heated and passed through powerful rolling mills that flatten them into thin sheets. At this stage, the sheets measure about 1/4 to 2/5 of an inch thick, but they're still too thick for most applications. After hot rolling, the sheets are cooled to stabilize their structure. If needed, they undergo annealing, a controlled process of heating and slow cooling to relieve internal stress and improve the metal's flexibility. For ultra-thin sheets, like foil or packaging materials, the aluminum goes through cold rolling, reducing its thickness to less than 0.04 of an inch. This precision ensures the sheets meet the requirements for various specialized applications. Once the aluminum is formed into the required shape, whether as wire rods or sheets, it's transported to factories or directly to customers for further use in manufacturing. Recycling aluminum requires significantly less energy compared to extracting new material from ore. In fact, recycling aluminum saves up to 95% of the energy that would otherwise be needed for mining and processing raw aluminum. To put it into perspective, it's like a 100-watt light bulb running for 4 hours. Here's another mind-blowing stat. If all the aluminum cans recycled in the United States each year were stacked end-to-end, they'd cover approximately 3,000 football fields. And if you combined the recycled cans from the US and Europe, they could wrap around the Earth twice. Imagine this, a house printed in just 24 hours. Sounds like science fiction, right? But it's real. Back in 2018, the United States saw its very first 3D printed house. Today, there are hundreds of these homes, and the numbers keep growing. This technology doesn't just build houses, it's redefining architecture with designs that are both stunning and efficient. And the best part? A home like this could cost as little as $10,000. Ready to see how a giant printer turns concrete into cozy living spaces? Let's dive in. The first 3D printed house in the US appeared in 2018. Now, there are hundreds of these homes, and the count is steadily climbing. Let's start with the basics. 3D printing is a technology that creates objects layer by layer using specific materials. When it comes to houses, this means a massive 3D printer extrudes concrete or other construction materials based on a pre-designed blueprint. Think of squeezing frosting from a piping bag, except instead of frosting, it's concrete, and instead of a cake, it's a fully functional house. These 3D printers are no small feat. They're massive. Imagine a structure the size of a small crane or a garage hangar. For example, Icon, a Texas-based company, uses a system called Vulcan. This printer stands about 11 feet tall and spans over 32 feet in width. Its modular design allows it to expand and adapt to the size of the house being built. The printer operates on rails or special platforms, moving around the construction site. That's why it can print anything from a tiny cottage to a spacious home. Essentially, it's like a large truck, a smart, precise machine that gets the job done with remarkable accuracy. Let me tell you about my visit to one of these construction sites. Icon, based in Texas, invited me to see their house printing process up close. And let me tell you, watching this gigantic printer in action makes you feel like the future is already here. It all begins with architects designing the house on a computer. It's like those 3D renderings you've seen in movies or on designer websites. Depending on the complexity of the design, creating a 3D model can take anywhere from a few hours to several weeks. A simple, single-story house without elaborate details might only take a day or two. But a complex project with unique shapes, energy-efficient features, or intricate interiors? That's a whole different ballgame. Here, architects work closely with engineers to ensure everything checks out. Will the walls hold up under pressure? Are the windows and doors positioned correctly? Are the local climate conditions accounted for? The coolest part? Modern software like AutoCAD, Revit, or SketchUp makes this process faster and allows for detailed visualization of every inch of the house. At the construction site, a massive 3D printer is set up. This printer, essentially a giant robot, moves on rails or with manipulators. It starts printing the house layer by layer. The main material? A special quick-drying concrete that becomes incredibly strong. Once the walls are done, the roof, windows, doors, and other elements are added. At this stage, traditional construction methods are used to finish the house. While the printer can handle the main structure, components like the roof, windows, and doors are typically crafted from traditional materials like wood or metal. For example, the roof might be made of metal or wood, depending on the project. Windows and doors are also custom ordered and installed using conventional construction techniques. This blend of innovative technology and proven materials ensures homes that are not only efficient, but also comfortable to live in. The entire process takes anywhere from a few days to a few weeks, a stark contrast to traditional construction, which can drag on for months. 3D printed homes have a ton of advantages, making them an increasingly popular choice. For starters, they can be built in just a matter of days. These houses are also significantly cheaper than traditional ones. According to Icon, a small home can cost as little as $10,000. And the designs? They're nothing short of art. This technology also minimizes waste and uses eco-friendly materials. Traditional construction often leads to a lot of leftover materials like concrete, wood, and metal, especially when cutting pieces for doors, windows, or walls. But with a 3D printer, materials are used only where needed. The printer lays down each layer precisely according to the design, leaving no excess material behind. It's not just about efficiency, it's about sustainability too. Many companies involved in 3D construction use materials that have a lower environmental impact. For instance, the concrete might include recycled components or be made with eco-friendlier ingredients, reducing pollution during production. Moreover, precise material calculations mean fewer resources are consumed, eliminating the need for extra stock or creating waste that ends up in landfills. This approach not only saves money, but also significantly reduces the environmental footprint of construction. The technology also opens doors to new types of eco-friendly materials, such as biodegradable concrete that incorporates recycled waste or organic substances. These materials reduce CO2 emissions and the need for extracting new resources. So, 3D printing isn't just speeding up construction, it's making it more sustainable and environmentally friendly. It's not just a trend, it's a real shift in the construction industry, one that could greatly improve our ecological outlook for years to come. Of course, it's not all perfect. The technology is still new and comes with its challenges. Currently, most 3D printed homes are made of concrete. But for more complex designs, new materials will need to be developed. These massive printers are also hard to transport and require specific conditions to operate. Plus, many countries don't yet have clear regulations for constructing such homes. Icon can print a house in just 24 hours. One driving factor behind this technology is its potential to address affordable housing shortages. 3D printing dramatically cuts costs on materials and labor. For example, Icon is working on a project to build homes for low-income families at just $4,000 each. The technology also unlocks incredible possibilities for architects. A 3D printer can create intricate, unconventional shapes that are almost impossible with traditional methods. Architects now have the freedom to design without limits, knowing the printer can handle any form or detail. The future of 3D printed homes looks incredibly bright. These technologies are already being used not just for housing, but also for offices, schools, and even hospitals. Icon is building the first fully 3D printed neighborhoods, including a project in the US in 2021 that delivered 5 homes to financially struggling families. And here's what blew my mind. Icon is working with NASA to print homes on Mars. Imagine that. One day, people might live in 3D printed houses not just on Earth, but on other planets too. Icon was founded in 2017 in Austin, Texas, by a group of engineers and entrepreneurs. Their goal was ambitious, yet simple: to create technology that makes housing fast, affordable, and sustainable, especially for those with limited access to traditional homes. The idea came when the founders realized the construction industry was bogged down by outdated methods and high costs for materials and labor. They envisioned 3D printing as a way to simplify the process, lower costs, and provide homes for those in need. Initially, Icon started as a small startup in the construction sector. It quickly gained traction and attracted major investments. Soon, Icon partnered with the Bjarke Ingels Group to create a groundbreaking 3D printed house, marking a significant milestone in the industry. This was the first house printed using technology that reduced material and labor costs. From there, they scaled up to build larger homes for various social programs. In the following years, Icon secured significant funding from venture capital firms, allowing them to improve their technology and expand production. For instance, in 2020, the company raised $35 million, enabling them to grow their operations and launch new projects.